Not for tomorrow, but like February, so that Dr. Jen. In other words, my boyfriend. You'll be at. Oh, I'm so. And the first part, which is pretty dang similar to our first paper, one of my colleagues asked if they could just like take information from there. If it has to be proven, you know. And he's like, yeah, you can take it, provide me with that.
All right. Regional campuses, Austin, check in. San Antonio. Hello.
We can hear you in San Antonio.
Dallas.
We can hear you in Austin.
Austin, okay, good.
I can hear you in Dallas.
Yeah, I can hear you in Dallas as well.
Can you hear us?
Yes, I can hear you in Dallas.
Okay, all right, very good. So we will start with tree-based methods. Next time we will talk about the midterm. Okay, so we finished grading, and we will have the discussion about the midterm. We'll discuss the answers and your grades as well Wednesday. Okay. And we will, we will post your grades first. So we'll publish the grades on Canvas so you can see your grade, and then we will have a discussion next time. All right. So tree-based methods, new methods, new approaches, and doing data analysis and doing classification and regression. So we can use them for both, for regression and for classification problems. Tree-based methods are really simple and easy to use, easy to explain, very simple, and they work. We can start with a simple tree, but then we will later on see how we can build on this simple tree. So we will have another lecture about trees as well, or tree-based methods, and they are very powerful. They're proven to be really powerful in a lot of supervised learning problems. So the basis for tree-based methods are actually, the basis of it is actually coming from what we call a decision tree. And a decision tree is more of a natural way for you to make a decision, for anybody to make a decision, is to formulate the problem that you have, that you need to make a decision on, in a set of rules, where you can answer a yes or no as a binary. And based on that, you will get to your decision. That's the answer at the end. So we'll see an example of a simple decision tree, and these are like the basis of building a tree for classification or regression. Okay. So involves the method in here involves dividing or segmenting your their observations using the predictors that you have, using the variables that you have for your observations, into segments or regions that are distinct, non-overlapping regions. The question here is like how to come up with those regions, how you can divide the space of your problem in here into those distinct regions. And basically the way you do that is that will define the rules that you can represent using a tree. And the name in here, tree, is just the way of representing or drawing the decisions in here. The rules, the set of rules that you have to make a decision. So before we go further, this is a very simple example of a decision tree. When you think about it, what to do on a weekend. You want to make a decision, like what's the plan for this coming weekend for you, right? So, basically you think about it this way. If I have a homework, if I have an assignment that is due, then you just need to stay in and do your homework and do your assignment, okay? So pretty much the answers is a binary tree, right? Let me just... Just a second. It's taking too long. Okay, so if your answer is yes, you stay home and you do your homework. And if the answer is no, then you will, think of something else, right? So pretty much that was like the first rule that, kind of you will have in your mind when you decide what to do on a weekend, is if you have something to do, a work to do. If not, then the next questions maybe is the weather is going to be nice outside, right? If the weather is nice, then maybe you will go to the beach, maybe you'll go to the park, you'll go outside, okay? But if the weather is not nice, then maybe you will, start texting your friends, who's out there, and see if they're available. If they're busy, then you may just stay home and watch Netflix, right? And if they're not, then you can get with your friends and go to the movies, because it's raining outside, so you can just go to the movies. So this is a simple decision tree. This is the basis of tree-based methods. They are simple, easy to use, and the model is the tree. So we call it tree, although it's upside down. So this is the root. This is the root of the tree. Okay, usually it's the other way around, right? And the nodes that you see in here, pretty much the ones that you use to make a decision, those are what we call leaves or terminal nodes. We call those leaves or terminal nodes. And the ones internal in here, where you have your rules, are the internal nodes, including the root. Okay, the root is just a name, but you have 1, 2 internal nodes, and including the root. So the root is internal. So you have 3 internal nodes, and you have 1, 2, 3, 4 terminal nodes or leaves. So this is the terminology of trees, or decision trees. And this is the model. There is no equation. That's why it's simple and easy, especially for non-statisticians to explain it to non-statisticians and non-data scientists or non-mathematicians. It's like this. This is it. So, really, nice and easy way to use, as an approach for classification or regression. Okay. Doesn't want to move. All right. I don't know why. So pretty much using this idea in here, we will try and find those rules from pretty much the predictors that you have to divide the space into regions, into areas, and basically also it's easier to explain using an example. And that's why we have this simple example in here. This is from a database, a data set, the Hetter's data set in the library that you have from the textbook. and it is about baseball players. So each dot in here corresponds to a baseball player. And we have the salary color coded in here. Okay, so we're looking at two variables. We're looking at the years of experience for each baseball player, and we're looking at the number of hits in previous leagues for each baseball player, and we color coded their salary. So the blue and green, that's low salary, and the red and yellow high salary. Okay. So pretty much you can see in here, the more years of experience a player has, we're expecting the salary to increase. So we're looking at, pretty much in here where we have a lot of reds and yellow, and also for the number of hits. So, pretty much if you think about it, the more experience the player and the more hits the player has, successful hits in previous leagues, we're expecting the salary to be high for those players. And the less the years of experience or the smaller the number of the hits, we're expecting their salary to be low. Okay, so this is the answer in here. Of course, the color coded is the answer for our problem. But we know it's a supervised learning problem, so we know the answers, or we know the outcome in here. Now, the question in here is, again, if we want to go back and think of in terms of a decision tree, the first question in here is to ask, as a rule, in your first node in this tree, is to consider one of those predictors, and you see if you can make a split or if you can divide this plot in here into two regions that are non-overlapping, right? Where it will be easy, or it will make it easier for you to distinguish between low salary and high salary for those players. So you need to think of a predictor that you will select, just one of those two, and a split that you need to make to draw the cut in here, right? To draw the line that can separate the high salary from the low salary. Okay? Now it doesn't have to be perfect, because we know, in many cases, like the case in here, is we have a lot of values and the colors in here that represents low and high, and they're not easily separable. But but they're pretty much if you look at the figure in here, you can kind of see that it's possible. You can make this plot, or you can make this split to just one at a time to separate low from high. Okay, so what do you guys think? Where would I draw this line to split the observations that I have in here for those players, to split them between, or to segment between low and high?
Around 5?
Around 5? Yes? Okay, so if we go in here, pretty much the 5 years of experience, and you see in here we have we see a lot of blue and green in here, right? And the rest of the area in here, we kind of have a mix of all colors, but pretty much the majority are yellow and red. A lot of yellow actually, right? So with one split in here, you divided this plot, or this, the observations that you have, the space of the observation you have, into two regions where you can kind of make a prediction using the predictor that you selected. If the years of experience less than 5, then we can predict the salary as low. And if it's more than 5 years of experience for the player, we can predict that the salary will be high. Okay? Now, again, you see in here just one split, but then the second region in here is a mix. So can we make it better? Yes? Can we make another split in either region? So you can also go back to this region and make a split. So do we need to make a split in here? It's kind of a lot of blue. We don't need to make another split. But for this region in here, yes, we can make another split to, kind of make it even further, even better for our problem in here to distinguish between low and high. So where is the second split going to be?
100.
Around 100? Do you guys agree? 100? So we're going to use the heads in here as the predictor that we will select. And then we can make a split, maybe around 100. Okay, and now we have another region, right? So we have 1, 2, 3 regions. So we split the space into 3 regions. And this is pretty much trees. So first we selected a predictor, that is the number of years of experience. And we formulate the rule in here if the number of years is less than 5. And in this case, it's probably 4.8. If it's less than 4.8, then the salary will be predicted to be low, right? But if it's higher than 5, then we need to look at the number of heads. And that's the second rule that we will have is if the number of heads in this new region is more than 110 maybe, then the salary is high. Else, the salary is considered in this case low. Okay. Now, if the problem is a classification, you need to see what is the majority class, right? So what is the majority class in here is low. So we classify to the majority class. If it's a regression problem, what do we do? If you are to predict a value, a salary value, what do you do? What?
Make a model and then just find the person, like their parameters, and then plug it into.
So if the salary is, if the years is less than 4.5, what is your predicted salary for anybody who has less than 5 years of experience? What's the predicted value? Well, I mean, that's a class, as a classification. But if it's a regression problem, then you need a salary value.
Oh.
So how do you calculate this value?
Mean.
The mean. The mean of the average value of all the observations. As simple as that. Okay. So in the case of classification, you just look at the majority class. Okay. Although in this case in here it's a mix, right? But maybe the majority is high, so you classify as high. And here the majority is high for sure because of the colors. So this region is high if you have only 2 classes, right? And this region is the majority low, so you classify as low for any observation that falls in, in any of those regions. And if we're talking about a value, then you take the mean, the average value of all the observations in these regions. So this is how we represent this in a tree. This is the representation of it, and this is the model. So the first question was years less than 4.5, and if it's yes, now usually in tree-based methods, the left, hold on, so this is the left, yes, is the answer yes. Okay, and the right side is no. Okay, yes, the convention in here for using trees or reading trees. So this is the average value. This is the average or the mean of all the salaries in the region where the majority are blue colors. Okay. So your prediction in here for any player who has less than 4.5 years of experience to have this salary. Okay, 165, 147. Now, if the years of experience is more than or equal, right, 4.5, then you go and ask the second question using the other predictors about how many hits or successful hits this player has, and then you go about calculating the average in each region. So you see in here we split the space into 3 regions, and pretty much following the tree in here, you will fall at the end to one of those terminal nodes, and the answer will be the average value for all the observations that you have in each region. Questions? Yes?
So I understand, like, when we were looking at the graph, visually you could see the different colors, but if you just had a problem and you were trying to make a tree, how do you know to split it by years first?
Very good question. So this is how, this is what we're gonna see next, is how to create a tree. I mean, in this case, it's, it's easy, but this is an example in here, right? Okay. But we will see how this is done actually, and you will be using the library for your R session programming. I will give you some examples. So how this is done actually, right? How, what's the process or what's the procedure of doing it? But what do you think? Before I go to that slide and talk about the algorithm that will create this tree, what do you think? What do you think? We have two predictors, and we are, for us it was easy to see that the split at this point will, differentiate, or will put all the blues in one side and all the yellow and red to the other side. Okay. Now, if those are not color coded, if they are all dark black, okay, but you have the outcome, you have the values, or you have the class, and that's all about it. So how do you go about selecting which predictor and what cut point, or where to cut? Should I start with years, or should I start with heads? And if I start with years, what year should I choose? What's the criteria in here that I need to use by which it will give me, the selection in here of a predictor and a cut point that will give me a good result at the end, or a good, accuracy at the end. How would you do it if you don't have any access to a program or a library to create a tree? Manual.
Without knowing their salaries?
No, you have the salaries. You know the salaries. You know the outcome, either a salary or a class of low and high. But which predictor should you select first to make the root and the cut point? In our case, it was years and 4.5. Why was that the first selection?
The variable which has strong correlation or strong relationship with the outcome salary.
How would you determine that?
If you plot your predictor versus response variable and see if they have a very linear relationship.
We're not, tree-based method doesn't work this way.
Based on the frequency.
Frequencies?
Frequency.
So you want to count how many?
Based on the year that are more. They can design the tree based on the years and find the frequency of the years and put on the root the year that has more frequency.
Yes.
I'm guessing baseball contracts. So usually a rookie contract at baseball is 4 to 5 years. So you can see if they're entering the league from a rookie status, obviously it's going to be lower because they got to prove themselves, and then you can see that cutoff point when they re-sign, and then obviously if they do well, their salary will increase.
So we don't have domain knowledge.
Okay, so
of the problem.
Okay.
So you just have numbers. Think about it. You have 3 columns. Yes, let's assume that you have 100 or 500 players. For each player, you have the first column, years of experience, the second column, the heads in the previous leagues, and the third column is the outcome, that's the salary value. That's it.
Would you always make these graphs first to begin with?
You can make a plot.
Because, having the plot, you can visually see, I don't know if the right word would be clusters.
You can call them clusters or groups.
That the colors are separated, but if you don't have that, then you're stuck.
The answer is easy. Come on, guys. Yes.
Why don't you test and see which one produces the lowest?
Correct. That's the answer. Just try. Try different values. You select the first 1 years and you try and cut at the first maybe year. Make your cut at year 1, and then you will have, kind of a measure, right? Of if it's a classification, then you have the error rate in the both regions, and you make another cut at year 2, and you compare it. So your goal in here is to have the less number of errors.
Right, but you already said you just started with years. How do you even start with years?
Well, you also, the same question here, you can also, kind of have more experiments where you can start with hits and then years.
That's a lot of work.
It's a lot of work, yeah. Okay? So that's what's happening in here is, basically your objective function, or your loss function in here, the one that you try to minimize, is the residual sum of squares, the errors. Okay? The misclassifications if it's a classification problem, or residual sum of square in the case of it's a regression problem. So your objective is to have a minimum value of either, depends on the problem, and based on that you will make your selections. Okay. So, but you don't need to do it manually, right? You can just run the program, and the program will do it for you. So the selection of years and the cut point 4.5 was the best criteria in here, okay, to select from, because it will guarantee the other cut points will not get you a better results or better, or less errors. Okay, sorry, more errors with classifications. Now, once you select a predictor and a cut point, that's it. You divided those two regions, so you're not going to go back to it. You're just going to move forward now, and now you have two regions, and you will think of dividing those two regions separately. So you don't, so you go one step at a time, okay? Or what we call the top-down approach. So this is just to explain the tree that we built from the plot and the terminology in here, right? So again, this is the root of the tree, and it's also an internal node, and this is also another internal node, and those are terminal nodes or leaves. And the values that you see in here is the average of all the observations that fall into this region. Now, each observation should belong to a region. And this is, if we run this example on R will, the simple tree that you will create in R will do these cuts. So the selection was actually 4.5, okay? And for the hits, it was 117.5. And we have those three regions. So again, if it's a regression, the average value in here is your answer. And if it's a classification, then it's a majority class. We take the majority class, and that's going to be your answer. Any questions about the terminology of the tree? We understand? Yes?
So the no, wherever we write no, those are the internal nodes, and wherever we write yes, those are the the corresponding values.
No. So the rules are the internal nodes. The rules or the questions. Okay? Because in here you can think about it as a question. The years are the years less than 4.5. It's more of a question. Okay, so your rules in here are questions, and a way to traverse the tree or to read the tree is the left is the answer to this as yes, and the right is no. So those
there are two internal nodes.
So this is two, yes. So this is an internal node,
and
the root is an internal node.
Okay, and this one is not.
And those are leaves or terminal nodes.
So there are 3 terminal nodes.
And 2 internal. Yes. And the answer is going to be in a terminal node, right? We know the answers in here. So these are formed by the predictors. It's going to be a predictor and a value. Another example for is also, just how to interpret. The interpretation of the tree results. That's all, when you build the tree in the game, the tree is your model, how to interpret this tree, and sometimes it doesn't need a lot of interpretation, right? You can just show it to anyone, any non-statistician, and they say it's kind of, it will explain itself, right? So, by the way, this slide will kind of summarize what we talked about. You can summarize it in just a paragraph as an interpretation of the result. Okay. So again, as you can see, the pretty much this is the model, no equations, nothing, and that's why trees are said to be very simple and easy to use and to explain. This is another example using olive oil data. You can find the data set. I will see which library has this data set. And using, pretty much 8, with some predictors in here, 8 predictors, to explain the contents of those olive oils, to classify the origin, okay, of the olive in which region in Italy. It's kind of one of those toy examples or early examples to explain the use of tree-based methods or trees. And it's just more of a classical problem. Again, like when we talk about the iris data set, that's kind of a classical problem in machine learning textbooks, where given measurements of the flowers, and you classify iris, and you classify them into the categories. So it's more of a classical problem. So the same thing in here goes for the olive oil data, based off the measurements of the contents of the olive oil. We can determine where this olive oil originated from, in which area or region in Italy, using trees. So the problem in here will be formulated again, using one predictor at a time and a cut point. So you select a predictor and a value, and then you make a split. It's always binary split, and you go further in the tree up to the terminals where your answer will be in a terminal node. So this is part of the tree where we have one of the measurements, one of the 8 measurements, and if the value is less than what we have in here, it will go and ask another question. But if it's greater than, we can basically determine it is from southern Italy. And now the second question in here, based on another predictor, and we have 2 answers where pretty much kind of explain. So it will be, for some problems, this is going to be easy, especially if they are well separated. So you see in the figure in here, if we only consider 3 regions, and as you can see in here, they are well separated, we can basically make a tree in here that can give you a perfect classification into 3 regions. So, and again, tree-based methods will be suited for this kind of problems. Now we know we learn linear regression. If you think about applying linear regression in here, or if it's a logistic regression, you will see that tree-based method will do a better job. Okay? And especially the case in here because the classes are well separated. And the way to go with, making the splits in here, okay, as like, or forming regions, rectangular regions, this is the only way you can achieve that is using a tree. It will make those rectangle or box splits. Same goes for the iris data. You can use trees, and you will pretty much again select. If we only select 2 measurements of the flower in here, just using only just two measurements, because the original data set has 4 measurements, we can make a tree that can make a classification based on those measurements into 3 classes. All right, so this is like how to visually, if you have a way to visualize or to make a plot of your data, and you have your outcome, especially if you are using only 2 predictors, right? Because you can visualize it. But we need to know the process, the tree building process for any problem. How do we split the space in here into those regions? And again, how many regions do we need? If you think about it, it's like, how many regions do I need? And where and how to select a predictor and where to cut this predictor. Yeah. So, if we are to, if we have this figure in here, back to this one, and it's not color-coded, how many boxes or how many splits you can make? If I ask you, let me ask you this in a different way. If I told you that we have 10 regions, okay? I want you to create 10 regions, and each region is a box, okay? Not a rectangle. You can have a region as any shape. It can be of any shape, right, if you think about it. But if we're using trees, it will be rectangles. But to make it simple, we will use boxes because they have the same length and width. So if I ask you to select or to split the space using only 10 boxes, where do you place those boxes? Okay. So it will, you need a lot of computation here to pretty much select or to place those boxes in this space, by which you will have good accuracy. And the problem in here will transform from box making or splitting this space into regions into more of what we call a greedy approach, a top-down greedy approach of one step doing the splitting of one step at a time. So, and that's what I meant before by once you select a predictor and a cut point, there's no going back. So you make a split into 2 regions. That's it. You need to think of the next step on how you make a best split of those 2 regions into further regions and go on with it. There's no going back to previous steps. So that's why we call it a top-down greedy approach. Our goal is to minimize the residual sum of square. So our goal in here is to make a j number of regions. That's the total number of regions that we will make. And in each region in here, our goal is to minimize the error, right? So that's the summation in here of the true outcome minus your prediction. The y hat is your predicted value, which is going to be the mean of the values or the observations in this region, squared. So this is the sum in a region R. And you sum over all. Okay? So if you have 3 regions, okay, so you have an error term or an error value calculated in each region, that's the residual sum of square, and you accumulate them, you take the summation. So our goal in here is to minimize for all the regions of the residual sum of square. So you want to think of where you place those boxes, okay? Yes?
Can you go back to the equation? What is the E? The I, E, or J under the sum? What's
So
really an E?
the capital J is the,
Thing
okay,
that looks like an E.
Contained in I N R C J.
Oh,
this one?
yeah.
N, contain N. Okay. Or belongs to, I belongs to R, J.
Okay. So you're saying for every observation that's in the region?
So yes,
Okay.
okay, for each observation in region R, you have the residual sum of square, and you sum over all the regions. All right. So the goal in here is to place those boxes, okay, by which you have a minimum value for this function or this equation. Now, if you go about, again, placing those boxes, this is going to be forever. It will take time because the problem will be, how to split and, where to make those splits. So we go and take a top-down greedy approach. You select one at a time, and then you go further with it. Okay, so the greedy means in here, greedy at the current step, like we don't care what's going to happen next. We care about the current step. What is the best split that I can make? What is the best predictor that I can select? And the best cut point that I can choose to, minimize the residual sum of square. Okay? At each step. That's why it's kind of greedy at the moment. So again, we first select a predictor X and a cut point S, such that the splitting the predictor space into regions will lead to the greatest possible reduction in RSS. And then after that, we go about the next predictor and the next cut point and so on. Okay. So you repeat the process for all. Okay, so this is the details of the process of creating a tree. And, the prediction in here is just, traverse the tree. Right? So go to the roots and see the first question, go with the answers, yes and no, until you fall into one of those terminal nodes, and you'll have your answer there as your prediction. Okay. No equation, right? You don't need to apply an equation. You just go to the tree and see where it falls. So this is another way, or another example, where pretty much given x1, x2, two predictors. Seen here, like if we assume that t1 was the first cut point that we made, or the first split, and then t2 is next, then t3, then t4. So we cut the space in here into 5 regions. Now for this, we can, that's how we represent this in a tree. Again, using the rules in here as our internal nodes. And pretty much you will see that each region in here is basically a leaf node or a terminal node. And if it's a classification, you see the majority class. If it's a regression, you calculate the mean. Now we can also have a plot. This is the plot in here of the answer, again using x1 and x2, or of the tree. And pretty much, this is where we made the cut points, right? T1 is basically at this point in here, and T2 will be at x2, so this is T2 in here, and so on. So it's, from the figure in here, we can kind of see that we're dividing the space into areas or regions, where at each region we have a constant. So it's a kind of a piecewise constant. If you remember, for previously the nonlinear models, we talked about the piecewise constant method for prediction. So it's kind of similar in here. The tree created piecewise constants for us. And at each region in here, the constant that we will have is the mean value. So any observation that will fall in this region or in this area, your prediction will be the constant value calculated as a mean for this region or this area. Okay. So it's like, kind of a way to represent, right? A different way of representing the tree in 3D.
Can we use a k nearest neighbor method or something to get these regions, or
to get what?
To get these type of regions? Can we use like k nearest neighbor or something?
It's a different approach.
Oh.
It's a totally different thing.
So are there tree-based methods that use a?
No.
No. Okay.
It's just totally two different things.
Okay.
It works in a different way. So tree methods, now it's basically just as simple as select predictor at that time, select a cut point, and the selection in here is kind of, you need objective function in your mind is to minimize the residual sum of square. So this is how we make the selection. It's like I want to select this now that will give me the minimum RSS at this step. Okay, so it's one step at a time. You don't look ahead more than one step. Yes.
Okay, is this a very flexible method or a very rigid method compared to any normal?
No, this is very flexible. Okay, so you can build a tree, and you can have a very large tree. Okay, that you can grow a very large tree to the point where you will have each observation in one node, on one region. Yeah, you can do that. You just, in here we stopped, right? If you think about it, if I'm going to go back to the baseball example in here, we just stopped at 3 regions. But, you can also go further. Like, we made the split in here, in this area, but then maybe I can, make another split to kind of isolate the blue from the yellow and go further and make more splits. And again, we'll rotate between years and heads, right? Because you only have 2 predictors. So you make, in each region, you can further make more splits and more splits up to the point where you can have, for each observation will fall into its own region. Now, whereas in this case, what do you think the training error will be?
Very high. I'm sorry.
Training
Training error will be low.
Extremely low.
Training error will be extreme.
Like, how extreme?
If there's only one terminal node for each observation,
Yes,
the training error is 0.
correct. Very good.
But the test error is
The test will be very high. Okay? So if we are going to grow a tree, a very large tree, to the point where you have your observations fall into regions, distinct regions, then you have a training error of 0. Because, each one has its own area. But this way is like, this is how we overfit the model in trees, is by growing large trees. So we are kind of just focusing on the training data and making it perfect for the training data, making the splits in here just corresponds to the training data, and we lose the generalizability of the model, giving a new test set, try and apply it, you'll have a very high testing error. Okay? So, when do we stop? So when you grow a tree, when you build a tree, do you want to go, like, how far do you want to go in growing the tree? Like, when do you stop the splitting, making splits? How did we stop in here in 3 splits? Go on. Okay, very good. There you go. So now you know the stuff. Cross-validation. Okay? So there is, again, so what we do is usually is we will add a parameter to our minimization function to penalize large trees. So we will go and explain it. But basically, you don't want to go build a big tree because it will overfit. And at the same time, you don't want to grow a small tree because it will be oversight, right? And here we will not, be able to, to do good in whether in training error or in testing error. So you want to build a tree that is just right. And to get to that point, you need cross-validation to determine, how big, how further you should go in making splits, or how soon you should stop in making splits. Yes?
So it seemed like in the beginning of the trees that each internal node was based on one predictor. If you were to make a bigger tree when you only have 2 predictors, I'm assuming then you can use the same predictor
Correct.
to make multiple.
Yes.
Okay.
Yes. If you select a predictor, it doesn't mean that you can't select it again. You can, further select the same predictor for further splits, of course.
So how does that relate to when you said once you make it, you can't go back? Like, so you can still use the predictor again, you just
Can't go and go back to the previous step and fix. Okay? Because again, your goal at the end is to minimize the overall error. But you can't calculate the error, you can only calculate the error at each step.
For the slide with the 3D graph, what is the z-axis?
That's the outcome. Yes. Assuming that's the outcome in here as a value. So the pretty much going back to how do we select a tree size that is just right? The answer in here is kind of one possible answer is to build a very large tree. Okay, just keep going with it, and once you have this large tree, you can trim it. So you can, that's the principle or the concept in here that we have in this slide is pruning a tree. That's trimming the tree. Okay. Now the trimming of the tree in here is from the leaf nodes and going, back. And the way to evaluate in here is the size is good now or no, is if you have a validation set. So you will have like a training set and a validation set, by which once you grow a big tree, now you can validate, okay, using the validation set, and then start trimming the tree, make it shorter, and then do validation, okay? And then go back even smaller and do validation and so on. So you kind of build large, go small, 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 and you have validation that you can apply, by which, at some point when you do it multiple times, up to a specific size, a small size, you can basically select which size among the different sizes that you cut is the perfect size for your tree. Okay, we understand the concept in here? So, to put it in an equation, again, our objective is to minimize the residual sum of square in all of the regions, but then we will add a penalty term, okay, to penalize the tree size. So this symbol in here, T between the bars, is the tree size. And alpha in here will be a tuning parameter, a penalty parameter. So the question here is like, what is the best value of alpha? To choose a value for alpha to penalize the tree size, because again, we don't want to grow. This is regularization. This is the same concept of applying regularization to our linear regression models. Is you want to penalize, okay, the model in here, and the penalty is going to be imposed here is for the tree size. We don't want it to go too big. We want it to be kind of relatively small. So you control in here how big or how small using this alpha parameter. How much penalty you want to give to the tree size. To choose the alpha parameter, we do the validation, the cross validation. Okay. So in other words, again, is just to build a large tree and start cutting it and do validation up to the point where you can determine which size is the best or the perfect size for my tree. And at this point, you have a value for your alpha. So when we go to using R, we will just run the function. The function will do that in the background. We'll just basically calculate alpha for you and determine the best size. Okay? But again, we will, at the beginning just build a very large tree without those tuning parameters. And because we want to see, the training error and the testing error. So this is, basically choosing a subtree inside your big tree, right? Because you have a big tree and you start cutting it, it means I want to select a subtree, a smaller one, from within my big tree to kind of give me a relatively good testing error. I mean, you predict the testing error using the validation, of course, because testing is going to be done at the end. Yeah. So this is what we call, again, the pruning the tree. The algorithm that I just described is called the cost complexity pruning, or the weakest link pruning. That's just a different name for it. And that's the equation that we kind of use or to represent this algorithm. Is we just add this regularization parameter, and choosing a value of alpha will be done through cross-validation.
So is the T? Oh, never mind. I just saw that. It's the number of nodes that you use. So you're multiplying alpha by your number of leaves. Okay.
So that's what we mean by the tree size. So the tree size is the number of nodes, terminal nodes in this tree. Okay. So you don't want your tree to have too many nodes. That's a large tree. So you want to penalize the tree size in here. You're going to give a penalty. Okay. And how much? You need to do cross-validation. Okay. So, think about it. You can think about it in a different way. Think about it as, okay, I'm going to grow a tree of size 2, or, the minimum will be 2, right? 2 nodes. And then try the size 3, 4, 5, 6, up to maybe 100. And then select the best one. It's kind of a similar way if you think about it. But we don't do it this way. We just grow a big tree, just keep going. Okay, there is a stopping criteria, and there's a default stopping criteria. In R, requires like a minimum number of observations in the node. Okay. Once you reach this minimum number, it will stop. So you have a big tree, and then you try and find the smaller tree or a subtree inside this big one that will have the best validation accuracy for us. Okay. So this is how do we choose the best subtree, and that's basically by cross-validation we will determine the value of alpha. Any questions? We good so far?
So would you call this tree method as linear method or non-linear?
It's non-linear.
Because the regions are kind of non-linear?
Yeah, it is non-linear. Okay. So this is, if we want to apply the pruning method on the baseball example, the baseball salary example, where we divided the data between training and validation. We grew a large tree, and then to select alpha, we'll do cross-validation, and that's pretty much. So this is the results in here, and we will see when we go to the R session. At the beginning, we will grow like a big tree. So you're just gonna run the default tree function. And it's, as you can see in here, it's bigger than what we've seen before. So using actually more predictors in here. We're not just using hits and years. We're using the other predictors. And this says pretty much if we do the tree pruning algorithm when we run the tree function, and we kind of record for each alpha parameter in here, which is going to be associated with a tree size, what is the training, what is the cross-validation error, and what is the testing error. So with a tree size 1, that's what we have, just take the mean, right? Tree size 1, it means just calculate the mean of everything, and that's going to be your predicted value. So what is the testing, what is the error, training, testing, and validation errors. And with tree size 2, 3, 4, and so on. So we all know that the training error will keep going down, and with the increase of the size of the tree, we'll see that it will keep going down, the training error. Okay, so if we're going to extend this, it's going to keep going down. And for the validation and testing, you will start to see that at some point they will start to go up, okay? Because that's where we will lose the generalizability of the model. So at the point in here, we will need to select the tree size corresponds to a good validation and testing accuracy. So it looks like, where is that? Like, what tree size would you select that you think from this figure is most appropriate? What do you think is the most appropriate tree size to select?
Three.
3? Do you guys agree?
I mean, technically it looks like 10, but do you still want to pick the less complicated?
Very good, yes. Okay. So I would pick 3. Okay. So 3 is where I still have a simple model and I still have a good validation and testing accuracy. Okay. So that's what happened in here is with the baseball, even, and also, very good that I just remembered one thing by going to this example. Although we have many predictors, and you will kind of notice that when you start working on the homework for this chapter, sometimes you have so many predictors in your observation for the data set that you have. When you build a tree, it doesn't guarantee that we will use all the predictors. Okay? It will select kind of the most important predictors. Because remember, at each time, the algorithm with the tree is going to select one out of all the predictors, and it will make a split using the values of this predictor that will kind of guarantee that this is going to have the most reduction in residual sum of squared. Okay. So in other words, like at each step, we will select the most important feature or the most important predictor. Okay. So we will have predictors that will not be selected, but which we can conclude that those predictors are not important for our model. And that's one of the really good advantages of using trees is the model itself, when you look at it, it will tell you which predictors are more important than others. Okay? So if we're going to go back to the example in here, yields is the most important predictor. Then heads and this predictor as well. Okay? But when we go into pruning the tree, trimming the tree, it turns out this is not important. Those predictors were, or this whole thing, it was not important, for example. Okay? So that's why when we cut the tree, we determined that the best size was 3, by which we just consider 2 predictors out of maybe 5 predictors. So it's in a way we are doing feature selection.
So in that tree diagram, can you say for tree size of 3, how do you decide, like as in what is size 3 means?
3 nodes, 3 leaves, terminal nodes.
Okay.
3 terminal nodes at the end.
Okay.
So you see this one in here? What is the size of this one? What's the size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Yeah.
Okay. How many terminal nodes do you have? Now, the case of classification, we call them classification trees now. Okay? Regression trees and classification trees. And the prediction in here is going to be for the most commonly occurring class, the majority class. Now, the classification settings, we don't use residual sum of square. We use the misclassification or the error, right? So the error rate, the classification error rate, or the misclassification accuracy, you can call it, right? And that's, if you think about it, if you go to each region, right? So in each region, you have number of observations, and if you have only two classes, class A and B, then you will have some of those observations in class A and some in class B. So you calculate the proportion of those two classes. Okay. Now, if 80% of those observations in this region in class A and 20% in class B, then your prediction for anything that falls in here will be class A, because 80% is greater than 20%. Okay, so the case in here, the E, or the classification error rate, is going to be 1 minus the maximum. So going back to the example that I have, in this region, what is E in this region that I just talked about? What is the value of E? If you have observations in this region, 80% in class A, 20% in class B. The majority is class A, and that's your prediction, right? That's your classification. So what is the value of E in this region? 0.2. Okay, so the value is 0.2. Because we're assuming that the observations that fall into this region that doesn't belong to the majority class are errors. That's the assumption in here. So this is the value E for this region. And then you need to accumulate for all other regions as well. Okay. So the objective in here is to minimize this E value. The same way we did with the residual sum of square is to minimize for all regions. The same in here is we're looking for a tree that will, at each step, you make a selection of a predictor and a split for the space of the values of this predictor that will guarantee that the E value and the terminal nodes that will result from this split will be minimum. Okay? So to minimize the E value in here. In other words, we're looking for terminal nodes that are pure. That's the best, that's the perfect, right? Is to have all the terminal nodes, all the observations in one terminal node to be of the same class. Okay, that's going to be guarantee a good classification in here, right? Or at least the majority of them to be in one class. So you can use the classification error rate as a metric to pretty much to minimize based on. And there are also other metrics that are, kind of better in statistics than the error as a misclassification. There is the GNI index and the deviance. The equation of both, and they both have very similar behavior or similar properties. Those are more suitable. It will have a more of a smoother properties. So the GNI index is pretty much to calculate the proportion in here of the values that will fall in one class times 1 minus this value. And you take the summation over all the classes. Okay, so again, P hat MK, okay, so that's the definition of it, this is the proportion of the observations in the mth region, so M is a region, that are from the kth class. And so you take this value, P, and if you think of one region where you have two classes, you have a two classification, A and B, okay? And if we assume that the observations that you have in this region, 80% in class A, 20% in class B, then the P value in here will be 0.8, okay? For class A, for class A, and 0.2 for class B. So the GNI index in here will be pretty much 0.8 times 0.2 for this region. As the value, if you just want to calculate the value in each region, it will be 0.8 times 0.2. Now you need to do that for all regions. And you take the summation. Let me give you an example. So you have, let's assume that you only have two terminal. Let's assume that you have, let me see if we have numbers in here. We can assume some numbers. So if we assume, let's just remove those, okay? Let's assume that this is a classification problem and we have two classes, low and high. And let's assume that the number of observations that you have, or the proportion, again, it doesn't consider the numbers, it's the proportion of how many of those observations in class A as a percentage. So let's assume that we have 80% in class A. That is, let's assume it's the low or high. 20% is in class B. Okay. Now, what is the GNI index in this region? Because you need to calculate for each region. The GNI index for this region is going to be 0.8 times 0.2. Okay, because you need to calculate for each. Why does this keep going? For each region. Now, if you have more than two classes, you will need to calculate for each class. It's going to be plus. Since we have two classes, it will be 0.2 times 0.8. Okay. So that's the G value in this region. What is the value in here?
Wouldn't that just multiply itself by 2?
Well,
Aren't you just doubling it then
yeah.
for each region?
Yeah, pretty much. This is how you calculate this. Okay? Now, if you have three classes, that's going to be a different story, right? If you have three classes, let's assume I have 70%, or let's do 0.7, 0.2, and 0.1. This is let's assume class A, B, and C. And then the G value is going to be in here 0.7 times 0.3 plus 0.2 times 0.8 plus 0.1 times 0.9. It's a simple equation. And you take the sum. All right. So if you look at the proportion of A and B in this region, if we just consider two classes, 80%, 20%, right? So it's kind of a, good proportion, 80-20. But of course, we need a value in here, the GNI index value, to reflect, as a, to have a value in here by which we can distinguish the pure regions from the non-pure ones. We want to favor regions where we're looking at the observations to be the majority in one class. So of course in here, if you think of 80%, 20%, and I will calculate the G value in here is 0.8 times 0.2. That's 0.32, right? So the G value in here is 0.32. Now, if I change the values in here into 90% and 10%, okay? I mean, we favor this proportion in here, 90-10, than 80-20. Because again, when you make a classification in here, you take the majority, and if the majority is, in your observation, fall into one class, it will, kind of be an indication that your testing error will be less. Okay? It means you made a good selection of the splits that you have. So if I change this to 90 and 10, what is the G value? What is that?
0.18.
0.8. Okay. So now the value is much smaller, okay, than the previous one. Now, what if I change this to 95 and 5? It will be even smaller. So, if we get to the point where G equals 0, where do we get that? How do we get G value equals 0? When all of them in one class. Okay? So this is, kind of a perfect scenario in here, where the splits that you made were able to have regions where the majority or all of the observations in this region are from the same class. So your classification should do good in this case. Your tree that you constructed, if all the terminal nodes have a very small G value, then you will have a very good accuracy, whether in your training or in your testing. I mean, testing you still have to test, of course.
So you're calculating a G value for every terminal node,
For
and
each.
then that determines if you're keeping that branch on the tree or not.
No, the G value in here is like a value that is similar to the misclassification error, a parametric.
And you want it to be as close to zero.
So you want to minimize, correct. So you want to, your objective function in here is going to be in terms of the GNI indices that you will calculate it, and the objective in here is to have a smaller G value that is close to zero. So you need to kind of make a selection of a predictor and a split that will kind of get you to a point where the G value in the terminal nodes that you will create are as close to zero as possible.
Right, but you have a different value for every node.
Yeah.
Right?
Yes.
So you're going through and basically redoing each model, and you're trying to minimize all the G values.
So
you just add them all up and try and get small numbers.
Again, you do it step by step. The process of building a tree is a step-by-step process. You don't just build it and then calculate. So at each step, when you want to make a selection and a split, you will kind of have different options. Okay, think about it. Different options to select which option is the best as a predictor and a cut point. You will make those selections and you will calculate the G value based on your selections, and then you will select the one that will have a smaller value that is close to zero. And then you move on to the next step in the tree.
I have one very basic question.
Yes.
So I understand misclassification error rate as, say suppose if you have two classes and you know the truth and you are predicting something and you see how many of your predictions are correct in both the classes, but here it looks like the misclassification, the error rate is, say suppose if one class is major,
Yes.
and you are trying to just subtract the 1 minus of the
1 minus the maximum.
But the first scenario, what I told, even if we have a major class and a minor class, and if we predicted everything correctly.
So it's not about a correct prediction in this case. It will all be all the observations in one region, okay? If you have the majority in class A, and you have just small observations in the other class, those small observations, we will consider them as errors.
Oh, okay. Here the error is not what we previously thought.
No, it's not the error of the misclassification, right? So we're trying to have in each region as many, like we're trying to have a homogeneous, like we're trying in each region to have as much as possible observations belonging to the same class. And anything else we'll consider as error. So this is like if we use this metric as our minimization in our minimization objective function, but a better metric is the GNI index.
But what if the data itself has 4 classes and all 25%?
So you accumulate them. So you take the majority. So this is, okay, very good question. So you have 4 classes, and let's assume that one of them is the majority. Okay? So one of them is, let's assume what, 0.5, and the rest will have 0.5. Yeah. So the error will be 0.5. So the accumulation of them.
Oh.
So you think about it as all in one class, the max, and everything else is not that class. So those are misclassified.
Oh.
That's why it's better to use the GNI index. When you have multiple classes, it will give you a better sense of how pure, and we call it the purity metric as well. How pure each class or how pure each node in terms of the different classes that you have. Questions before we end today? We will continue next time. Tree-based methods. Very simple. It's a very simple method. It's one of my favorites, tree-based methods. I mean, not the tree, but the forest. We'll go there. It is called a forest. It's building many trees, or growing many trees. And a very, very effective and very good method in machine learning, forests. All right, so we'll see you next time then. You have questions? You guys want to wait for the questions, or? All right, we'll see you next time. We'll discuss the midterm and we will finish this.
You're always going to have
Correct.
So, and you have one
Yes.
but so if you go there and try after that, I will make.
So you have one node and you branch off and you create a two and you calculate the G in each one. Yes. And based on that, let's assume that this was one scenario or one experiment. And then let's assume that there is a different split using a different predictor that gets you two different G values.
Really?
So you kind of select the one that in total is less.
Here? Or are you adding them together?
You will add them together, yes.
I think so.
But
Between the two branches?
between the two branches. Yes.
So you're minimizing the total number.
No, because you're not comparing like the comparison here between two selections, and in this case you need to calculate the sum.
I mean, I don't even agree.
Because on here,
Yeah.
I just want to pass this class. No, I really don't. It's like when there's the three classes. Like
Yes.
literally, like I want to plan, but then I just want to be.
Yeah.
Yes.
See what I'm saying? But
Yes.
then if sometimes I'm not that. Yeah, I just need. I know, but I keep looking at this.
Yes.
Every decision you make. When you wear them,
Okay, exactly, because the choice of your predictor and the cut point that you made in here gets you to 2. Exactly. You take the sum, and then you compare this in the process of building a tree. We'll compare this with a different cut point of the same predictor, or maybe a different predictor altogether. But one step at a time, one level at a time. So once you're done, you make a selection.
I wasn't.
Pretty much.
I mean,
That's it. You move to the next step and so on and so forth.
The one I showed you is definitely right for at least one.
It's a very simple model.
Everybody already got it.
Yes.
yeah, I just.
Okay. So let me show you as an example. Okay. You see, when we change the equation here to penalize the tree size, we kind of need to determine like how much we want to penalize, like how much we want to. Like this is gonna affect the tree size. Now, what is the best value for alpha? We don't know, so we need to kind of try different values. In other words, like we need two different sizes. So the figure in here is like we don't choose the tree size, we choose alpha, and alpha will determine the tree size. Okay? So we're kind of running different experiments with different alpha value, and each one will be like kind of a tree size. And then within the cross validation, you will kind of determine which one will be the lowest validation. That's why they done. Yeah. So anyway, once we go to the using the functions and
Your meeting has ended.
there is a simple, there's a simple way. Validation.
I want to go to the hospital if they were they really need their respiratory and they die.